In Chapter 2, we're going to be talking about measures of central tendency and dispersion, as well as z-scores, which is kind of how we measure dispersion. So in Chapter 2, we're going to talk about the mean, variance, standard deviation, and z-scores. So when we're talking about finding the middle of a group of scores, we're talking about measures of central tendency. And we're going to focus on mean, median, and mode. When we talk about measures of dispersion, we're looking at finding the spread of scores, which is measured by the variance and the standard deviation. A way to talk about how spread out scores are in a standardized way is by using z-scores. So we're going to be talking about z-scores as a way to discuss numbers of standard deviations that a particular score is away from the mean. So something that we need to talk about first is that in this class we use what are called conceptual formulas. They are formulas that are used to reinforce the concepts that we're talking about as opposed to the mathematical computations. You will arrive at the exact same answers. There's no difference there. It's just reformatted or rearranged in such a way that you learn how to do each concept in the formula as opposed to just plugging in a bunch of numbers and getting some number that magically appears. So there is no difference in what you get. We're just using a computational formula as opposed to the mathematical formula. So, or the computational formula. So we use them because they're easier to learn to reinforce the concepts, and because the symbols that we will use in our formulas are more widely used in social science research. We're going to talk about some symbols that we will use and maybe some ways that they are a little bit different from what the book says, because this edition uses a couple different symbols that we will talk about that we'll have to kind of unlearn as you read it. But I'm sure it'll be okay because you will see that the symbols are synonymous with the concepts that they cover. Let's jump right into it and talk about the mean. And with the mean, median, and mode, I don't want to spend a whole lot of time talking about them because presumably you've seen this before. So for the mean, median, and mode, we have, those are the measures of central tendency. The first is the mean. Sometimes you've seen it as what's called X bar, with X with the line over the top, or we're going to use capital M for the mean. And the formula for the mean is the sum of the scores divided by the number of scores. So as you can see, the symbols mean something. The uppercase sigma, which looks like kind of a funky E or a backwards 3, that's a uppercase Greek sigma. It means the sum of. So when you see that, know that you're adding everything together. So it's the sum of X. X is each score. So we're going to take the sum of each score divided by N, which is the number of scores. Those are your first three symbols that are used formulaically. I guess M is also a symbol, but formulaically it's the sum of all the scores divided by the number of scores. So let's try an example, and we're going to try an example of the mean ages in a college classroom. And I'm just going to throw out some numbers, and we'll probably do this in class with actual numbers, but for the sake of this lecture, let's throw out some numbers here. Let's say that we have 5 people in the class, just for the sake of making it easier. And the ages of the people in the class are 21, 19, 19, 20, and maybe 24, a non-traditional student. All we need to do is add these together because that's our formula. The formula is mean is equal to the sum of the scores divided by the number of scores. So the sum of the scores is 21 plus 19 plus 20 plus 4. So if I wanted to just rearrange that, all of our x's are 21, 19, 19, 20, and 24. And our n, by the way, is equal to 5. So let's go ahead and we have our scores. Let's go ahead and add them together. So we're kind of building this formula. So the sum of 21 and 19 and 19 and 4 is 21 plus 19 is 40, plus 19 is 59, plus 20 is 79, plus 24 is 103. Okay. Now the next step that we take, let me erase that, is to take the sum of the scores divided by the number of scores. So the sum of the scores is 103. I'll put a line in there. Is 103 divided by 5. Okay? 103 divided by 5 is 20.6. So in this example, the mean age of the 5 people in that class is 20.6. Oops, lost my marker. Okay. Now, the next measure of central tendency is the mode. The mode is the most frequently occurring score. We usually use the mode when we're talking about nominal variables, but we can also use the mode for our last example as well. What we normally do with the mode is we create either a frequency table or a histogram. The histogram will indicate the mode by the tallest bar. A frequency table will be the frequency that has, or will be the value that has the highest frequency. Let's just go ahead and use the data from last time. So we're going to take the mode of the age of the people in the classroom. And what we're going to use is the ages from last time. So let's go ahead and plug those in for our values. We have, just bringing it forward, 21, 19, 19. Let's see, there was 20 and 24. So our range looks like it goes from 19 to 24. So we're going to put our values 19, 20, 21, 22, 23, and 24. The frequency of 19 is 1, 2, 2. The frequency of 20 is 1. The frequency of 21 is 1. There is no 22. There is no 23, and there is only 124. If we wanted to plug in our percentages, we could do that. So let's see, 40% of the respondents had a 2, 20% had a 1, a 21. I think I misspoke before too. 40% of the people are 19 years old, 20% are 20, 20% are 21, 0% are 22 and 23, and 20% are 1. So in this particular case, the most frequently occurring value is 19. We can tell that from the frequency table. We're not going to do a histogram. This histogram just kind of boring looking for this data because there are so few points. So our mode would be equal to 19. You can have multiple modes, by the way. So let's say that there were 2 people who were 20 years old, and if that were the case, then we would go from the frequency of 1 to the frequency of 2. Whoops, the frequency of 2. And if we did that, then obviously the number would go up here, and it would be 40%, and then whatever. Okay, so the mode could be 19, and it could also be 20. I will give you a hint. In SPSS, if there are multiple modes in a frequency histogram or a frequency distribution, it will tell you what the lowest mean or mode is. Good gravy. Let me start over the sentence. In SPSS, it will report the lowest mode if there are multiple modes in a frequency distribution. So in SPSS, it would report only 19, and it would have a little a superscript note that would say that the lowest of the multiple modes is indicated here, and then you have to go through and find out what the actual other modes are. I go over that in the data analysis for this chapter. So that's the mode. Let's go down to the median. And the median is the middle of a group of scores if they are sequentially arranged. This is important. The median, or the median requires that the data be sequentially arranged. And it's not just about counting in the same amount of numbers from each side, although you can do it that way. There is a formula to it. I'm not going to bother with doing that right now. We'll talk about that in class when we do examples of it. But the reality is that if we have our distribution from before, which was 19, 19, 20, 21, and 24, The median is the middle of the group of scores. So if there are 5 scores, the median of our distribution is 20. That is the middle of the group of scores. If there are many numbers, then we can use our formula. But generally, we're going to just rely on our descriptive statistics anyways. But the median is the middle of the group of scores. We use the median usually with ordinal variables. So those are the rank order variables. Or for variables that have values that are far away from the mean or far away from the middle of the group. We call those outliers. So if you have a scale variable like this variable is a scale variable, you can use the median if it has an outlier. Otherwise, you use the mean as the main measure of central tendency. So let's talk a little bit about when we use the mean, median, and mode. Here's a handy table that you can copy down. And we typically, for nominal variables, use the mode as the measure of central tendency. For ordinal variables or for scale variables with outliers, we use the median. And the mean is what we use with scale variables. And you'll recognize that if we use the mean on a nominal variable, something like your favorite color, because favorite color is not arranged in a particularly meaningful way, you're taking the mean of that won't be very interesting. The same thing as race and ethnicity. I see a lot of people try to say what the mean race or ethnicity is, and that doesn't make a lot of sense. We typically would use the most frequently occurring race or ethnicity if we were interested in something like that. And we wouldn't use the median either. We'd use the mode for nominal variables like race and ethnicity. So make sure that when you are reporting the meaningful measure of central tendency, you are referring to this, or mostly the box here, to guide you on which measure of central tendency is most reasonable for the variable that you are measuring. Let's look at an example. So we have, on a scale of 1 to 7, what your feelings of preparedness are when entering college, where 1 is the least prepared you could be and the 7 is the most prepared you could be. So we're going to use these and calculate the measures of central tendency that we've talked about. So for the mean, we are going to use the same formula. We're going to use the same formula, the sum of the scores divided by the number of scores, which is equal to the sum of all these scores divided by the number of those scores. So let's look at the number of the scores. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 scores, so I can just put that here. It's okay. N equals 10. So the sum of those scores divided by 10. So we can just add it up. We can do 5 plus 6. Okay. So 5 plus 6 is 11, plus 7 is 18, plus 4 is 22, plus 4 is 26, plus 2 is 28, plus 1 is 29, plus 5 is 34, plus 6 is 40, plus 5 is 45. So the sum of those scores is 45 divided by 10 equals 4.5. So on average, the people in this distribution had a preparedness rating of about 4.5, which is pretty much in the middle. The median is going to be the middle of these numbers if we sequentially arrange the numbers. So let's go ahead and sequentially arrange them. So let's see, the lowest number is 1. And then let's see, we have 1, 2. And what's next? We don't have any 3s. We have 1, 2, 4s. 4, 4. Cross those out. And we have 1, 2, 3 number 5s. 1, 2, 3. And then we have 1, 2, 6s. And we have 1, 7. Now, we know that there are 10 numbers here, so we know that there are going to be 2 middle numbers because, you know, if you count in the same amount of spaces or whatever, or use the formula, we're going to come up with 2 middle numbers. So here's what we do. We have 2 middle numbers. The 2 middle numbers are 5, which is nice because it makes the math easy. But when we have 2 middle numbers, we take the average of, or the mean of the 2 middle numbers. If we use our formula, the sum of the 2 numbers, which is 5 plus 5 divided by the number of numbers, which is 10, we get 10 over 2, we get 5. So we can use our mean formula to figure that out, although we know that it's just 5. So in this particular case, the median score is 5. Now the mode is the most frequently occurring score, so we can do just a quick frequency frequency table to figure this out. And I think what I'm going to do is I'm going to delete this so that I can make some space. And there we go. So let's go ahead and just quickly replicate our frequency table. And I'm going to take it from an earlier slide here. Bear with me. Kind of a peek behind the scenes at how this kind of thing works. And let's go ahead and make it smaller. That will work. And we can drag you down. There we are. Okay, so we have a scale of 1 to 7, so we need to list all the possible values on our scale, which is 7. So 1, 2, 3, 4, 5, 6, and 7. And the frequency for each one is listed. So let's see, we have 1. The number 2 occurs once. There are no number 3s. The number 4 occurs twice. The number 5 occurs 3 times. The number 6 occurs twice. And the number 7 occurs once. And we know that there are 10 scores, so each unit is worth 10%. So the frequency of 1 occurs once, that's 10%. And that's 10%, 0, 20%, 30% of the time, 20, and 10%. So this is an example of how we can do our frequency table. And what we can do now is we can look down and see which frequency or which value occurs most frequently. The value of 3 occurs most frequently. So the value of 3 becomes our mode. So our mode equals 3. Okay. Pretty simple, but it is important that you understand the basic idea of how and why we calculate these things the way that we do. Now, when we have the measures of central tendency, that tells some of the story about our numbers. It tells us that we have some kind of middle of our frequency distribution. And what we need to do is also talk about how spread out the scores are. We're going to look at an example on the next slide of how you can have the same mean but different spread of scores. So let's take an example. Let's say that we have a class which only has 3 people in it for the sake of making the example small. Let's say that we have a class of 3. The average of the exam could be 80%. And let's say that there are 3 classes and they all have an average of 80%. But that means that some of the scores could be 70, 80, and 90. Those could be the 3 scores and still average to 80. We could also have scores that are 100, 60, and 80, and they still average to 80. Or we could have 95, 90, and 55. So even though those 3 classes of 3 people have the same mean exam score, the spread of the scores is very different. Okay? So what's interesting about this is that we have to understand what variability is in order to understand how we compare groups of scores to one another, because we will be able to compare apples to oranges in this class. It'll be kind of fun. So here's what this might look like visually. So all of these frequency histograms have the same mean. They all have a mean of 8, so the average score is 8 for each of these. But as you can tell, we have this kind of mostly normally distributed histogram shape with the standard deviation close to 1, 0.97, meaning that on average each score is 1 unit away from the mean. Okay? On quiz 2, we just call it quiz 2, the standard deviation is 2.13. Which means that on average, each of these scores is just over 2 points away from the mean. And then we have a very taller peaked or leptokurtic distribution. And what that means is that even though the mean is still 8, the scores are very centered around the mean, meaning that we have a very low standard deviation. It's less than 1. It's almost 1/4 of a point on this exam. So you can see that we need to talk about the spread of scores in order to talk about the whole story of a group of scores. So variability is composed of 2 measures, variance and standard deviation. Variance is the squared average distance of the scores from the mean. That doesn't mean a whole lot at the moment, but you'll see what we're talking about. We do have to do some calculations in order to arrive at this number, but once you understand the idea of what we're doing, the calculations won't seem so daunting. And the other good news is that we don't really rely on these calculations when we're doing all of our inferential testing after the first exam. We will be using it for the first exam, but after that, we're not going to rely on the hand calculations so much. We'll rely on SPSS. Now, when we have the variance of our distribution, that's the hard part. The easy part is going from the variance to the standard deviation, and you'll see what we're talking about here in just a moment. So, variability is composed of two measures, variance and standard deviation. The first measure is variance, and it's related to standard deviation. It's pretty easy to find standard deviation after the variance. But the variance equals the sum of all the scores minus the mean squared divided by the number of scores. So here's what that means. The sum of all, remember that's that summation or that capital sigma. The sum of all the scores minus the mean, so you take each score and subtract the mean from it, and then you square it. You add them all together. So the whole top line is subtract the mean from the scores, you square that value, and you add them all together. You'll see what I mean in a minute. Then you divide all that by the number of scores, which is n. And the symbol for variability is SD squared. It's actually standard deviation squared, interestingly enough. So we can move on and look at an example. When we break this down into the steps, it makes things go so much easier. So when we break this down, we find all of our scores first, all of our scores minus the mean. We take all of our scores minus the mean and square them. We add them all together. We divide them by the number of scores. At each step, we have names for them. X is our score. That's just all the scores in the distribution. The deviation score is how far away our score deviates from the mean. So if our score is above the mean by 1, it has a deviation score of 1. If it's below the mean by 2, then it has a deviation score of 2. When we square those deviation scores, we get what are called square deviation scores. It's a clever name, right? Then the next step is to add them all together. So what we do is we take the sum of the squared deviation scores, and we get what's called the sum of squares. So we take the square deviation scores, add them together, we get the sum of squares. It's abbreviated SS. That becomes very important later on. The next step is to find the average distance that each sum of square is from the mean, and we do that by taking our sum of squares and divide it by the number. I think I said taking each sum of squares and divide it by n. We actually take each square deviation score, add them together, and then we divide that by n. Pardon me. Let's take a look at an example to kind of solidify this. Let's say that these are the scores on a particular exam. We're interested in knowing the mean of the scores and also what the spread of the scores is using the variance. So let's find the mean first, and let's find out how many scores there are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 scores. And the mean of those scores is equal to the sum of the scores divided by 10, which is 900, dividing it by the number of scores, which is 10, so the mean equals 90. I like to put that down here. And the number of scores is equal to 10. So the next step is to find out what our deviation scores are by taking all of our scores and subtracting the mean from them. So 85 minus 90 is negative 5. 90 minus 90 is 0. 90 minus 90 is 0. And I'm just going to go ahead and fill these in. 5, 0, negative 2, 5, 10, negative 11. So these are our deviation scores. These are how far each of our scores deviate from the mean. We need to square these numbers, and I'll tell you why. If we just said to ourselves, well, why don't we just find out how far each of our scores are from the mean, our deviation scores, and take the average or the mean of those numbers, because that'll tell us how far each score is from the mean. On average, we'd be in good shape. Well, here's the problem. If you added all these numbers together, you would get 0. Now think about that. The mean is the middle of a group of numbers, meaning that all the numbers on the top and all the numbers on the bottom, when we talk about the mean, so all the numbers above the mean, all the numbers below the mean, should be equal. That's what the mean is. So if we added all these numbers together, we'd get 0, and 0 divided by anything is 0. Now, one way we can get away with that is by squaring the numbers. We can take the numbers and square them. Some people think, well, wait a second, why don't we just take the absolute value? If you're thinking that, good for you. That means that you're kind of thinking about how these numbers work. That is one valid way of finding a measure of dispersion, but that's not how it works in statistics based on the way that we will use variance later on in the course. There are particular aspects of statistics that kind of are incremental in terms of complexity and what we use them for. And we need the variance later on, and that's what we use for central tendency, or excuse me, for dispersion in some very elaborate statistical analyses. We won't get into them in this class, so unfortunately it's one of those situations where you'd have to trust me. But we will use variance as a way to calculate our dispersion, and we do that by using our square deviation scores. So we take each of these scores and we square them. So -5 squared is 25. And by the way, when you're doing this on a calculator, you shouldn't get negative numbers. If you do, what you're probably doing is using the minus sign as opposed to a negative sign, or you're not including the negative sign in the parentheses like you should be. So we got 25, 0, 0, -2 squared is 4, 5 squared is 25, 0, 4, 25, 100, and 121. So those are our square deviation scores. So these are our deviation scores times themselves. Now our next step is to add all these together. And when you add all these together, you get 304. So the sum of the square deviation scores is 304. This tells us the sum of all of our square deviation scores, but we want to find out the mean deviation for each of these. So in order to find variance, which is our next step, we take 304 divided by n, which is 10, and we get 30.4. Now, conceptually, this is a little bit funky because 30.4 is not a very interesting way to look at our dispersion. Obviously, the average score of 90 is not going to have a standard deviation of 30.4 unless there are just some very spread out scores, but that's not the case here. If we were to interpret that figure, 30.4, as a standard deviation, what we would be saying is that the average distance that each score is from the mean is 30.4. That's obviously not correct because, let's see, no scores are farther away from the mean than 11. So let's see, the score of 79 is 11 units away from the mean. So how could the average possibly be 40? Well, our next step undoes the squaring that led to this inflated value. Remember back here when we looked at our square deviation scores? We have to undo that because we artificially inflated the distance that each score is away from the mean, which led to an inflated value in the variance. The way that we undo that is by using the next concept called standard deviation, which is a very simple step. So let's take a look at the formula, then we'll get into the step for it. Standard deviation is the next step after variance. Standard deviation takes the variance and reduces it back to a proportionate number. So instead of having a spread of scores that is equal to 30.4, we're going to have a spread of scores that more accurately represents the actual spread based on our distribution. So another aspect of variability is standard deviation, which is what you're most commonly going to report. Standard deviation equals the square root of the sum of all the scores minus the mean squared divided by the number of scores, or the square root of the formula we looked at when we looked at variance. So if you take that square root out, that's variance. If you put the square root back in, that is standard deviation. The only step between variance and standard deviation is to take the square root of this variance to get the standard deviation. It's a very simple process, but what it does is it reduces our proportion from a squared measure of dispersion to a standard measure of dispersion. So let's take a look at our example and see what that looks like. I've plugged in the information from the previous slides now that we've discovered it. So we have the number of scores is 10, the mean is 90. We have all of our deviation scores, all of our squared deviation scores. We have the sum of the squares. We have the sum of the squares divided by the number of scores, so it gives us the average distance. Each score is from the mean, but it's a squared distance, remember, because of the squaring we did back here. And then to undo that, we take the square root, and what we find is that the standard deviation of that distribution of scores is 5.51. The interpretation of the standard deviation is that on average, each score in this data set is 5.51 units away from the mean. So on average, you could expect, well, maybe I shouldn't say it that way quite yet, but on average, each person is 5.51 standard deviations away from the mean. So the average distance each score is from the mean of 90 is 5.51. Z-scores allow us to talk about how far away raw scores are from the mean. What's interesting about z-scores is it allows us to take scores from any kind of distribution, whether it's age, it could be height, it could be IQ scores, and compare them to one another, to be able to talk about how far away a raw score is from the mean, to know if an IQ of 120 is much more extreme than a shoe size of 12. It's interesting to think about that because we've known for so long that we cannot compare apples to oranges, but z-scores allow us to do that through standardization. When we want to talk about how far away a particular score is from the mean, we can talk about it in terms of the number of standard deviations away from the mean a score is, or we can talk about it in terms of the z-score. A z-score and a standard deviation are the same thing. A z-score measures the number of standard deviations away from the mean a particular score is. From our previous example, the mean was 90, and the standard deviation was 5.51. If you had a score of 95.51, that means your score would be 1 standard deviation above the mean. It would also mean that you had a z-score equal to +1, because remember, a z-score is just a measure of the number of standard deviations away from the mean a particular score is. So here's something to know about z-scores. Z-scores are continuous. What that means is that you can have a z-score from 0 to possibly infinity in either direction, so positive infinity, negative infinity, and the number of scores between z-scores is theoretically infinite as well. What that means is that you could have a z-score of 0, 1, 2, or a z-score of 1.1249362, and any number in between. You can have z-scores of any particular number. The mean of all z-scores is 0. So in this particular example, the mean z-score is 0. And I've put a normal curve on top of it, even though we won't really get into that until next chapter. But z-scores have a mean of 0, which is indicated by the middle of a normal curve. And the standard deviation of all z-scores is 1, meaning that when you go to the right by 1 standard deviation unit, that means it's a z-score of 1. So the standard deviation of all z-scores is 1. If I told you that you had a score that was 2 z-scores above the mean, I would be saying that you had a score that is 2 standard deviations above the mean. In our prior example, even though you probably couldn't get a score that high, a standard deviation above the mean, so if we had a mean of 90 from the prior example, a standard deviation of 5.51, the score that is 1 standard deviation above the mean would be 95.51. Let me just jot that down so you can visualize it. So from our exam scores, which is based on our raw X scores, we had a mean of 90 and a standard deviation of 5.51, so it would be 95.51, and then 101.2. Okay, obviously you couldn't get that, but the way that we calculate this is by taking our exam scores, which was 90, and adding a standard deviation to that. And our standard deviation was 5.51, so 90 plus 95.51 is 95.51. 95.51 plus 5.51, so one more standard deviation, is 101.2. And by the way, it works in reverse too, if we went backwards. So it'd be 84.49 and 78.98. That's just from our prior example. Let's convert our focus to IQ scores. So let's say, for the sake of argument and reality, that the mean of all IQ scores is 100. What that means is that the IQ that you have is exactly what you're expected to have based on your chronological age. But the mean of IQ scores is 100, and the standard deviation of all IQ scores is 16, meaning that if you had an IQ that was one standard deviation above the mean, you would have an IQ of 116. It's represented here. So the raw score for IQs is 68, 84, 100, 116, and 132 on our Z scale, or on our raw scale, which according to our Z scale means that a score of 100 is our mean. It has a Z score of 0, meaning that the score of 100 is 0 standard deviations away from the mean. And that makes sense because 100 is the mean. The score that is 1 standard deviation above the mean is 116. We get that by adding the standard deviation of the IQ scores, which is 16, to our mean of 100. That gives us 116. That is equal to a standard deviation, or a Z increase, of positive 1. If we add one more standard deviation to that, we get 132, which is the same as adding another standard deviation to our Z scale, which is adding 1, which gives us 2. So a mean of 100 on our IQ scale leads to a Z score of 0. A Z score of 1 is 116. A Z score of 2 is 132. And again, it works in reverse because this is a symmetrical distribution, which goes negatively in terms of the Z scores. So if you had an IQ score that was 1 standard deviation below the mean, you would have an IQ of 84. If it were 2 standard deviations below the mean, you'd have an IQ of 68. Now, interestingly, we can compare apples to oranges, or in this case, shoe size to IQ. Now, again, this is a fictitious example, so please don't get bent out of shape. I hope you don't think that your shoe size really relates to your IQ. When we have a Z scale, it allows us to do what's called standardize. We can standardize our scales according to one singular scale, which is called a Z scale. So if you had a shoe size of 7 in this example, you would have a mean shoe size. You would also see that if you had an IQ of 100, you also have the mean IQ. So if I asked you a question, which is farther from the mean, an IQ of 100 or a shoe size of 7, you would say they are both the same, that you have an average IQ and an average shoe size. So let me ask you another question. If you had a shoe size of 9 and an IQ of 108, which of those is more extreme? That means which one is farther from the mean? A shoe size of 9 is 1 standard deviation above the mean. An IQ of 108 is somewhere between 0 and 1 standard deviations. So it would have a Z-score between 0 and 1, but our shoe size of 9 has a Z-score of 1. So we know that our shoe size of 9 is more extreme. A shoe size of 5 or an IQ of 132? Well, a shoe size of 5 is -1 standard deviation, so it has a Z-score of -1, and an IQ of 132 has a Z-score of +2. When I say more extreme, I mean which one of those is farther from the mean. The IQ of 132 is more extreme, it is farther from the mean. Next example, an IQ of 68 or a shoe size of 12. An IQ of 68 is 2 standard deviations below the mean. A shoe size of 12 is off of our scale. It looks like it's going to be somewhere in the neighborhood of 2 to 3 standard deviations above the mean. Now that's actually 2.5, but it's still, we can estimate it between 2 and 3. So if I asked you which is more extreme, an IQ of 68, which has a z-score of -2, or a shoe size of 12, which is above a +2, you would say that the shoe size of 12 is more extreme. A shoe size of 5.5 or an IQ of 90, a shoe size of 5.5 is somewhere in the neighborhood of 0 to -1. An IQ of 90 is also in the neighborhood of somewhere between 0 and -1. That's not as easy to figure out. The good news is that when we don't have an IQ or a shoe size that falls right on the standard deviation line for us to compare more obviously, we can rely on a formula. We can convert our raw scores into z-scores to compare them. We do that by using a formula. The formula in order to find a z-score is to find out how far the score deviates from the mean. So we find our deviation scores, and then we divide it by the average distance that each of those scores varies from the mean. The formula as read is the z-score is equal to the score minus the mean divided by the standard deviation. Let's look at this in practice and make some more sense of it. Let's take a quick look at how we can use the z formula in order to determine how we got our z-score equal to 2 from our example with IQ scores. So let's go to the continuum so we can look at where we got our raw IQ score of 132. So 132 is the standard deviation +2. That's because the standard deviation of all IQ scores is 16. 100 plus 16 is 132. That means that it has a z-score of +2. Let's look at the calculation to see how that works out mathematically. When we plug in our formula, we take our raw score of 132 minus the mean, which is 100, divided by the standard deviation, which is 16. So when we plug into the formula, we get 132 minus 100 divided by 16. Z equals 32 divided by 16. Z equals 2. So an IQ of 132 has a has a z-score of +2. Let's go back to the example where we compare our shoe size of 5.5. So our shoe size was equal to 5.5. And we're going to compare that to our IQ of 90 to see which is more extreme, because they both kind of fell between 0 and -1 standard deviations. So let's start with shoe size. Z is equal to 5.5, which is our raw score, minus the mean, which was 7, divided by 2, which was the standard deviation, which is equal to -1.5 divided by 2, which is equal to -0.75. So about 3/4 of a standard deviation below the mean. So for shoe size, we can go ahead and plug it in. I'll just write it here, The shoe size that we're interested in has a z-score of -0.75. So somewhere in this neighborhood. Now our IQ of 90 is going to be set up the same way. Z is equal to 90 minus 100 divided by 16, which is equal to -10 divided by 16, which is equal to -0.625. So -6.25, we look at our IQ scale, is going to be somewhere in this neighborhood. So an IQ equal to 90 is going to have a z-score of 0.625. A shoe size equal to 5.5 is going to have a z-score equal to -0.625. Excuse me, shoe size was 5.5. It was a z-score of -0.75, pardon me. Now, when we look at this, we recognize graphically, but also numerically, that the number that is farthest from 0 is negative 0.75, meaning that our shoe size of 5.5 is the more extreme score. So in this case, if you had an IQ of 90 and a shoe size of 5.5, your shoe size is actually further away from the mean than the IQ is. And we can make that conclusion based on the fact that we converted our IQ and shoe sizes to z-scores and compared them on the same table. We have some additional exercises if you would like to practice and convert for yourself. So we can go through these real quick. If you want to work on them by yourself, you better stop the video now. So here we go. For our first example, we have 110. So an IQ of 110, how many standard deviations away from the mean is that? Or another way of saying that is, what is its z-score? So formula is z is equal to, maybe I'll put the z formula up here. Z is equal to x minus m divided by the standard deviation. In this case, our x is 110 minus the mean of 100 divided by a standard deviation of 16, because the standard deviation of all IQ scores is 16. The mean is 100. That is equal to 10 divided by 16, which is equal to 0.625. So we've seen that one before. So our z-score, if you have an IQ of 110, is 0.625. Let's move down and we'll work with 82. Same formula. Z is equal to 82 minus 100 divided by 16. So we're going to find out how far away the score is from the mean and divide it by the average distance that all the scores are from the mean. So that equals negative 18 divided by 16, which is equal to negative 1.125. Z is equal to 143 minus 100 divided by 16, which is equal to 43 divided by 16, which is equal to 2.6875. You could easily round that to 2.69 if you'd like to. So those are three examples of how we can convert raw scores to z-scores. Now, there is another application here, and we're going to briefly discuss how we convert z-scores back into raw scores. And algebraically, all we really need to do in order to find a formula to convert a z-score to a raw score is to take our z formula and then solve for x. So if you're mathematically minded, you'll follow this logic and we'll get down to x equals z times sd plus m. So in order to find a raw score from a z-score, we take the z-score, we multiply it by the standard deviation, then we add the mean to it. If we are inclined to try an example, we would kind of undo what we did from before and say, what is the raw score of an IQ z-score equal to 2? So if you had an IQ z-score that was 2, you would know that you're working with a mean of 100, standard deviation of 16, but a z-score equal to 2. So what we want to know is, even though it's there, what is the IQ score, the IQ raw score, if we have a z-score equal to 2? We use our formula. The raw score is equal to the z-score times the standard deviation plus the mean. X is equal to 2 times 16 plus 100. X is equal to 32 plus 100. X is equal to 132. For what we're going to do in this class, it is not incredibly relevant for us to calculate the raw score based on a z-score, but it is important that you understand the concept behind it because it will be applicable if you're going on and doing stats in other realms. Here's some examples that we can try. So let's go ahead and run through these and stop it now if you want to work through it on your own. In our first example, we can plug in the formula, and I'll go ahead and replicate the formula again here so that we can see it visibly. So the formula to find the raw score based on the z-score is equal to, or is x is equal to the z-score times the standard deviation plus the mean. So we plug that in. x is equal to the z-score of 1.45 times 16 plus 100, which is equal to 23.2 plus 100, which is equal to 123.2. So if you had a z-score of 1.45, your IQ would be 123.2. For negative 125, x is equal to negative 1.25 times 16 plus 100, which is equal to negative 20 plus 100, which is equal to 80. So if you had a z-score of negative 1.25, your raw score, your IQ, would be 80. And the last example, x is equal to negative 0.5 times 16 plus 100, which is equal to negative 8 plus 100, which is equal to 92. If you had a z-score of negative 0.5 on an IQ scale, you would have an IQ of 92. Now that's pretty much covers everything that we need to know in Chapter 2. I know there's a lot to cover in there, but it's important that you understand mean, median, and mode, that you can calculate standard deviation, which you will calculate variance along the way, and you understand that we standardize raw scores in order to make comparisons among multiple scores, especially when they aren't measured at the same scale. If you have any questions, feel free to reach out. Otherwise, use this to complete your chapter guides and to complete your data analyses.